aggregating medical data has the potential to revolutionize healthcare, and that applies to pathology images as well. But there are several well-known risks associated with this aggregation exercise. Privacy concerns, data security, bias and inequality. What about consent and ethical use of patient data? Data quality and integrity? What about the GDPR and regulatory compliance? The list goes on and on and on. So how can we solve it? How can those risks be mitigated? Well, how about if instead of aggregating data for training deep learning models, we just don't? How we don't? Then we're not going to have all those benefits. Well, we can. There is a method to do it that skips the aggregation steps. It's called swarm learning. In this video, I'm going to tell you about the concept of swarm learning for decentralized artificial intelligence in cancer histopathology, and it's going to be based on this Nature paper by Oliver Saldanha et al. This is a group from Germany. So what is swarm learning? It's a version of decentralized learning. You might have heard about federated learning. So when you train a model for histopathology, you need this model to see a lot of data, a lot of images, a lot of patterns to be able to later classify the patterns and everything the model saw well. And so far, this has been done with centralized learning, where the researchers would aggregate a lot of data and then develop model on this data within this data congregation, data library. And this has concerns, especially privacy concerns. So training clinically useful AI models requires the central repository, or at least it was requiring a central repository so far. And there are the problems, because in practice, this data sharing, especially across different countries, faces legal and logistic obstacles. So because we have different data privacy regulations in different countries, and one entity is aggregating all this stuff, all this data, and others have to comply with what this one entity governance is. Another problem is that this data is taken from different institutions where patients consented to give this data. But when this data is taken from the original institution to the institution that is aggregating the data, that is making the repository, this may require the patients to forfeit their rights to data control. This problem has been tackled by so-called federated learning. And in federated learning, multiple AI models are trained independently on separate computers, peers. So instead of aggregating the data together and training one models, we have several models on different data sets, and then those models communicate and exchange the weights and biases, but they do not exchange any data that it was trained on. So one could think, well, okay, problem solved. We now have those little models trained, and then they communicate, and we have this one big model that knows everything. The problem with federated learning is that there is a central coordinator that governs the learning process based on all the trained models, and they monopolize the control and commercial exploitation. This may be good, bad, depending on the ethical framework, and there's always a lot of investment going on. But if we want to have this even more independent, even more cybersecurity proof, and even more fair without any one entity being able to monopolize the process, this is where swarm learning comes into play. So in the last 2 years, the limitations of federated learning has been addressed by two different decentralized learning methods, one of them being SL, swarm learning, and the other one is the blockchain federated learning. So how is it done? Similar to federated learning, in swarm learning, models are trained locally and models are combined centrally without requiring central coordination. And how is it being done? It's being done by blockchain-based coordination between peers. So peers are those different models that are being trained on different data sets, and then they communicate via blockchain to combine all the knowledge they gained into one very smart model. So let's have a look at the image here. So it's happening here. We have our whole slide image. We divide it into tiles. We tessellate it, normalize, and we have several image tiles. We do feature extraction, and we train the classifier. And in this case, the classifier was a predictive classifier. It was predicting the MSI microsatellite instability status and BRAF mutation in colorectal cancer. And here we have the prediction map. The red ones were mutated and the blue tiles were classified as wild type. And then when we do aggregation for the slide, the label is mutated. So this is happening in each of those 3 places. What are the 3 places? 3 places are the 3 data repositories that we work with. So one was an EPI 700 data repository in the UK, the other one was DAX in Germany, and the other one was the TCGA, the Cancer Genome Atlas from the US. And we have different numbers of cases with the mutations, depending on where the slides came from. It was 600, over 2,000, around 500, depending which data repository the slides came from. And the training of those single models, so each of those data repositories had a model trained, and then those models communicated with each other via blockchain-based communication. And to keep this thing even more secure, they were trained on so-called bare metal servers. What are these bare metal servers? It's a kind of dedicated server, but whereas in cloud computing you usually deal with a virtual machine, here you have a physical machine that is doing the work and it's being used just for this training. You can rent this machine and pay for it. It's part of the new cloud computing services. And we can train those models in the basic way here, where the number of epochs is equal for all cohorts and weights are equal for all cohorts. Or we can have so-called weighted swarm learning, where the weighted SL, the number of epochs, is larger for small cohorts and weights are smaller for small cohorts. And for weighted swarm learnings, the number of epochs is larger for small cohorts and the weights are smaller for small cohorts. So which one was the biggest one? The biggest one was the DAX from Germany. So that would have lowest number of epochs but highest weights, whereas this small one would be the lowest weights and higher number of epochs. So what was the point of this study in the first place? The point was, and that was also the result, to show that swarm learning can be used to train AI models for pathology on par with centralized learning, which has been done so far. So how did the researchers show that SL is on par with centralized learning? So they used a retrospective multicenter study to predict genetic alterations directly from colorectal cancer histopathology whole slide images, where they tested all models on external cohorts. So like we said, they trained the local AI models on each of the 3 training cohorts separately. Then they compared it to the performance of a merged model. There was a merged model which was trained on all 3 training cohorts on a single computer, not on 3 different computers. And then they compared the performance of the merged model with the performance of the 3 swarm learning AI models. So when we look at figure 1, we can see that there were external validation sets, one of them called Quasar, and the other one was YCR BCIP from the UK, both from the UK. And this is where the models were compared. The particular models trained on the smaller data sets, merged model that had access to all those data sets together on one computer, and the swarm learning model that was based on blockchain communication between the 3 little models. So the conclusion here is that the swarm learning trained AI models outperform most locally trained models and perform on par with models that are trained on the merged data sets. And in addition, they showed that swarm learning AI-based models are data efficient. Let's explore that, because I was expecting that, okay, if it has the information from all the data together, and if this framework is legit, then it should be on par with the centralized model. But why would it be more data efficient? So it turns out that swarm learning could compensate for the performance loss that occurs when only a small subset of patients from each institution is used for training. So normally the more data, the better the model learns, but in order to have this big data, you need to aggregate them. Whereas here, with swarm learning, even if the local models are trained on small data sets, when they come together to communicate and create this one very knowledgeable swarm learning model, it doesn't matter that each of them was training on a small data cohort. Another thing that was noticed is that swarm learning model learns plausible patterns. What does that mean? That the tiles that were classified as positive for a particular mutation, when a pathologist looked at them, they actually saw features, histopathological features that were corresponding to that mutation. For example, in many cases, there was histological phenotype known to be associated with either BRAF mutational status of or MSI, and for example, mucinous histology or poor differentiation, which is great. But we also have a case of cancer where we have some features that are associated with a mutation. It's not a given. It's not that every cancer has features that are visibly verifiable by a pathologist that is associated with some mutation. So here they had a way to confirm it by a pathologist. It's not always going to be the case. And when I read about these things, I'm always thinking, wow, if this is so great, why is it not widely used? Why is everybody still trying to aggregate data? Is it because all the data aggregation initiatives initiated before this was known? Why are they not switching? Because it's so much more privacy friendly. And I don't have answers to these questions. So my goal is to actually invite the first author, Oliver Saldanha, to a podcast episode. So stay tuned. And if you do want to listen to that episode, leave me a comment below and just write podcast, and I will know that you want me to invite Oliver to the podcast. And I talk to you in the next episode.